Long-term pumping tests are a convenient tool for characterizing the distribution of properties that affect the transmission and storage of water in aquifers. What I mean by this long-term pumping test is that this is a test that would last longer than an hour and typically might last as long as a few days. These tests are used to stress an aquifer and evaluate how it responds to stresses, and then the response is interpreted to characterize the distribution of these properties. To understand what I'm talking about, we should first review transmission and storage properties of aquifers. So, a transmission property is a property that controls the volumetric flux per unit of head gradient in an aquifer. So, here's a simple sketch of an aquifer, and I'm implying that it's a confined aquifer. So, this is a boundary here where we don't have any flow crossing that boundary. And we can see that there are two piezometers in this aquifer, and this is the piezometric surface up here. So we have a head gradient, and that is inducing a flow that would go in this direction. And the flux that we get per unit of head gradient is going to be related to the hydraulic conductivity of the aquifer. That's really the definition of hydraulic conductivity, is the flux per unit head gradient. And the hydraulic conductivity can also be related to the permeability. The permeability is a property of the aquifer material itself, and the hydraulic conductivity is a property of the aquifer material and the fluid flowing through the material. But in most cases that we're interested in, the fluid is water. So we can relate the hydraulic conductivity and the permeability, knowing the fluid properties. The transmissivity, that's the hydraulic conductivity. If I use big K for the hydraulic conductivity, big K times the aquifer thickness, B, shown here, is equal to the transmissivity. And these are basic properties that we can determine these actually from short-term pumping tests. But what's going to happen is that if we conduct a longer-term pumping test, then we might be able to evaluate how these properties are distributed. So maybe there are some boundaries or zones where there are different regions with different transmission properties. The storage properties of an aquifer, these control the release of water from storage due to a change in head. And there are two important mechanisms that will be at play to release water from storage. If we look up here at this illustration, we can see one of them. So I've drawn this as a confined aquifer, and again, the idea is that this layer prevents any water from crossing it. So I've used a symbol here to indicate that this is clay or shale. And what happens then is if we have a piezometric surface up here, this piezometric surface, the height of this surface, is a measure of the pressure of the water in this aquifer. So if we pump some water out or somehow otherwise drop the pressure, then the aquifer will be compressed and the water will expand. So dropping the pressure will release water from storage due to these two compressibility effects. So when we have a confined aquifer, the release of water occurs from compressibility. And it's both the compressibility of the aquifer and the compressibility of the water itself. Now, in this other illustration here, this is a bit different because in this case, we have a water table here, and this is the surface where the pressure head is equal to 0. It's atmospheric pressure at that surface. And so what happens in this case is if we drop the water table to here, then these pores are saturated. And if we drop the water table, then these pores may partially drain from water. So the water that was in storage in these pores is removed from storage, and air enters these pores. Now, what happens? We have to also keep in mind that there's water in the vadosome above the water table up here, and when we drop the water table, some of this water may also drain out. There's a capillary fringe here, and the capillary fringe will drop down. So we may also release water from storage up in the vadosome. So releasing water from storage due to draining of the pores, where the water drains out and air enters the pores, that's this additional mechanism of releasing water from storage. And it really only happens when the water table is involved. So those are two important storage properties. And one thing that this points out is that the piezometric surface here, even though I draw them using the same symbols, the piezometric surface and the water table, they really mean different things, because this piezometric surface characterizes the pressure in this confined aquifer. So when it drops, that means that the pressure in the confined aquifer changes, but there's no pore drainage that occurs. However, the water table, when this drops, this indicates that in the vicinity of the water table, and above it, there can be pore drainage. And so generally for a unit drop of hydraulic head, pore drainage is going to give you a lot more water released from storage than this compressibility effect. But both of them will be important for different applications. So for a long-term pumping test, we're going to try to get an idea about the distribution of these properties, and also the distribution and the importance of these two different types of storage. Let's take a look at some of the basic principles involved in interpreting a long-term pumping test. So I just have a sketch up here of a simple aquifer, and what I want to do is take a look at what happens when we start pumping here, and we start pumping at this well here, and we get a drawdown as a function of the log of time plotted down here on these axes. So when we first start pumping, we're going to get a bit of drawdown in the well, and that'll cause some drawdown here, and the piezometric surface will drop, and that will propagate away from the well. So right now we've affected, say, this much of the aquifer. We've dropped the pressure, and we've released water from storage as a result of that. Now, the drawdown that we see, let's just say we've got a monitoring well out here, and the drawdown in that monitoring well is plotted here. So the drawdown that we see is going to reflect the properties within this region where the pressure has been affected. So it's going to reflect the properties within that region. It won't be affected by properties out here beyond the region that's been affected. Okay, so at early times, what happens is that the drawdown that occurs in the well is going to really just be affected by the properties of the well and right in the vicinity of the well. So you can imagine that right when we turn on the pump, the water that gets pumped out of the well first will be water that's just stored in the borehole. And if the permeability in the vicinity of the well is low, then we may have most of the water pumped out, particularly at the beginning, be water that's just stored in the casing itself. Okay, so the drawdown at the earliest of times in the pumping well, is going to be affected by the well itself. And this is wellbore storage effect, and also skin around the well will will play a role at early times. But as we keep pumping, the drawdown spreads out and affects a larger portion of the aquifer. And fairly soon we'll have a region like this, or let's assume that it's fairly soon. And the drawdown then that we see at this pumping well will reflect the properties within that region. And if we just say that this is an idealized aquifer and it's uniform, um, at this point we don't really see any effects of the edge of the aquifer. And if it's uniform, then what we're going to have is a behavior that is typical of a uniform layer of infinite lateral extent. This is represented by the Tice solution and the Jacob's approximation. And this is also called an infinite acting radial flow condition, or IARF. And so the drawdown as a function of the log of time for this case is going to look like this. There'll be some early time when this is the drawdown at the monitoring well. So there'll be some time here when the pressure front that's propagating out from the well has gone this far. There won't be any drawdown in the monitoring well. And then at some point right here, that pressure front, the drawdown front, will reach the monitoring well, and then we'll start to see some drawdown. And it'll curve upwards at first. And then one of the characteristics of infinite acting radial flow is that it goes and becomes a semi-log straight line, as I'm showing here. Now, the slope of this semi-log straight line and the intercept here along the x-axis, we can use to calculate the transmissivity and storativity of this layer. And since we're assuming that it's uniform, this would be like an average transmissivity and storativity. Okay, so that's what happens at relatively early time or intermediate time. And then if we keep pumping, this area that's affected by the drawdown expands, grows out laterally. It goes out to here. And if the well, or if the aquifer is uniform, then it's going to keep on progressing. And we could have really a couple of things happen to change this, because nothing's going to be uniform, or nothing's going to be infinite forever. Nothing's going to be infinite. There'll be some kind of a finite limit to it. It'll end. And one thing that could happen is that the reservoir could just simply pinch out. So I've kind of drawn this as maybe this is a sedimentary layer, and so maybe this is just the end of the layer. It wasn't deposited over here, in which case the drawdown would propagate out, and it would hit the edge of the aquifer right here. And when that happens, if we project this out, this is what would happen if the drawdown was, or if the layer was indeed infinite. But if it hits a boundary where the aquifer is no longer present, then what's happening is what will need to happen is the drawdown will need to increase faster than it would otherwise in order to remove water from storage, because we're assuming that we're pumping here at a constant rate. So if we hit a boundary, if the drawdown hits a boundary that is a no flow boundary or an edge of the aquifer, then the drawdown is going to need to increase compared to what it would be if the reservoir was infinitely acting. Okay, and along that same line, if the if we have here this stream, and let's say the stream is, I mean, this is kind of a reasonable way for streams to look, perhaps like resting on top of the aquifer. But let's say that just in an idealized case, the stream cuts down like that. It cuts all the way through the aquifer, and the head in the stream is right here, and the stream then holds the head in the aquifer equal to the head in the stream. In which case, when the drawdown propagates out to the stream, the stream could potentially lose water to the well. In which case, we wouldn't have to have additional drawdown to provide additional release from storage, and so the rate of increase of the drawdown could diminish. So we could have a change in the slope like this. So let's see, this would be a no flow boundary. And this would be a constant head boundary. And what can happen is we can keep pumping, and eventually the leakage out of this stream could be equal to the flow rate out of the well, in which case we can have the heads just level out and we go to steady state. Okay, so steady state by definition is a condition where the heads are no longer changing. So interaction with a constant head boundary like a stream could cause the system to go to steady state. Okay, so those are two scenarios that could occur as a result of the drawdown caused by the well interacting with a boundary. So there's some other things that could happen, and one of those would be if we say that, what I've been talking about so far has been kind of tacitly assuming that this is a perfectly confined aquifer. And what I mean by that in this context is that when I'm pumping out of this well, the drawdown caused by the pumping of the well is really just confined to this layer. Well, and that certainly could happen, but what's going to happen in a lot of cases is that, and we might imagine in just an end member case, say that there's not really a confining layer there at all. In which case, when I first start pumping, the drawdown may be covering this area, and then as I continue to pump, maybe it looks like this, and like this, and like that, and right at this time, this is now the region that's affected by pumping of the well. And at this point, the region that's affected, say where the pressure has dropped, has reached the water table. Okay, this case is now where we have just a uniform aquifer, an unconfined aquifer. So at early time, up to this point where the pressure has been affecting just this region, then we just have release of water from elastic storage because we haven't really reached the water table yet. But as soon as we reach it here, when it starts to propagate out like this, then we're going to start to drop the water table, and we're going to have in this region release of water from storage due to drainage of the pores. Okay, so that's an additional mechanism that's going to release more water from storage due to a unit of drawdown than would be occurring if we just had elastic storage. Okay, so what's going to happen then in that scenario is that if we have an unconfined aquifer, then we might have something like this where the drawdown goes along the same path up to this point, because as we're pumping, we have just initially we have just the drawdown is confined to this region here. It hasn't really affected the water table. Of course, it's not really just infinitely acting radially, so it's not going to be on this line per se. It's going to be slightly different because remember when we did this line, we were just having it the drawdown confined within this layer, so it'd be a little bit different. But my point is that once we go from, well, my point is that at early on, we're gonna have the drawdown affected by just the elastic storage. But then once we reach the ground surface, or once we reach the water table, the drawdown will, the rate of drawdown will start to diminish because we're going to have water released from storage as we start to drop the water table. So what that means is that we're going to have this flatten out. So as we start to have the water table become involved and drop and release water from storage, we just don't need as much drawdown as we would otherwise to generate this much flow. So we have a flattening of the drawdown. But what's going to happen then is, this drawdown is going to keep progressing out, and we'll have more drawdown of the water table. That's going to release water from storage, but we're going to continually have to expand this region and have more drawdown to release water from storage to pump it out. So it's going to, the slope will flatten, but it'll never get to be horizontal, never get to be constant, because we're going to continually need to have more water released from storage. And then eventually what's going to happen is that this water table will drop, and we'll get the water released from storage here, and then it's going to have to start, it's going to curve up, and we're going to have additional drawdown to release sufficient water from storage to satisfy this pumping rate criteria. Okay, so this would be, let's say, a poor drainage, and so this would be a switch from say elastic storage to poor drainage. So this would be a case where we would have an unconfined aquifer. Okay, and one thing that we see is that in both the unconfined and the this curve here that represents the pumping test that interacts with a constant head boundary, we have a flattening out of the slope. Okay, and also in all of these cases, we have an early time when nothing much happens, and then it starts curving up, and we have the possibility that it goes to a semilog straight line, and that semilog straight line would be an indication of the properties in the vicinity of the well. Even for an unconfined case, that may happen. We may be able to get an estimate of the properties in the vicinity of the well from this early time. It'll really depend, though. Well, yeah, a lot is going to depend on the details of the well design. If the screen is if the screen is well below the water table, then this time period here may be long enough to fit without really having an interaction yet of the water table. Okay, so those are some effects that we might expect to see in a long-term pumping test, and really these effects here are the kind of things that we hope to see and hope to learn about, and they're really one of the motives for doing this, for extending the term of the pumping and going to this long-term pumping test.